Welcome back to the channel Analytics Hub. In today's video, we'll be learning about one of the numerical methods of partial differential equations, which is known as FDM, Finite Difference Method. Before we move on to that, let's do a quick revision on PDE. So what is PDE? Partial differential equation is a mathematical equation that relates an unknown function of multiple independent variables to its partial derivatives. PDEs are typically classified by two main traits: order and linearity. Order is the highest derivative present in the equation. For example, if an equation contains del square u over del L square, but nothing higher than that, then it is known as a second order PDE. And for linearity, a PDE is linear if the unknown function u, let's say u is a function of s and y, and its derivatives only appear to the first power and are never multiplied together. E.g., there is nothing like u multiplied by del u del s or del u del s all raised to power 2 in the equation. Then it is known as a linear partial differential equation. A partial differential equation is quasi-linear if it is linear in its highest order derivatives. This means it may be non-linear in its lower order derivatives. For a second order quasi-linear partial differential equation with two independent variables s and y, the general form can be written as a multiplied by u subscript ss plus 2b multiplied by u subscript sy plus c multiplied by u subscript yy, which is equal to the non-homogeneous term which can be a function of s, function of y, function of u itself, or function of the derivative of u, or function of the derivative of y. And this notation here can be written as this, that is a multiplied by del square u over del s square plus 2b multiplied by del square u over del s del y plus c multiplied by del square u over del y square. So where u is the unknown dependent function, which means u is a function of s and y, u subscript ss, u subscript sy, and u subscript yy are the second order partial derivatives, and a, b, c are the coefficients. Now, classification of PDE. To classify the PDE, we use the discriminant b squared minus 4ac. The equation is said to be elliptic if b squared minus 4ac is less than 0. For example, the Laplace equation is known as elliptic partial differential equation. And the equation is also said as parabolic if b squared minus 4ac, the discriminant, is equal to 0. Example of this is the heat equation. And it is hyperbolic if b squared minus 4ac is greater than 0. Example of this is the wave equation. Note, in the heat and wave equations, the independent variable y is treated as time, t. The general form of the second order quasi-linear PDE can be written as, so I wrote it out again. Now, we want to confirm if Laplace equation is actually elliptic. So writing out the Laplace equation, we have del square u over del s square plus del square u over del y square equals 0. Now compare this to the general form of a second order quasi-linear PDE. Looking at this, we will observe that the coefficient of del square u over del s square here, which is similar to this one, a is equal to 1. Now the second term here, the second term in this general form is missing here. There is no partial derivative in respect to s and y, so it is b is equal to 0. That is the coefficient of 2b equal to 0. And for the third one here, it is similar to this one also. The coefficient here is equal to 1, c is equal to 1. Now when we input these three values into the discriminant, b squared minus 4ac, b is equal to 0, that is 0 squared minus 4 times a is 1, c is 1, so this gives us minus 4. And actually minus 4 is lesser than 0, which is the condition. The condition says that if b squared minus 4ac is lesser than 0, then the partial differential equation is said to be elliptic. Now for a heat equation is given as del u over del t equals to del square u over del s square. So in this place, we will treat this t, time, as our y variable. Now if we cross del u over del t to the other side. So we can have del square u over del L square minus del u over t equals to 0. Now I will compare this to the general form of the second order quasi-linear PDE also. We will observe that our coefficient a, which is this one, is equal to 1. Now for the second term in the general formula, it is missing here, so b is equal to 0. Even the third term is also missing here, c is equal to 0. Now when we substitute that into the discriminant b square minus 4ac, we have, since b is equal to 0, so we have 0 square minus 4 times a is equal to 1 and c is equal to 0. This gives 0 in total. Therefore 0 is equal to 0 according to the condition for parabolic PDE. So each equation is an example of a parabolic PDE. And for the third one, wave equation, the formula is the equation of a wave is del square u over del t square equals to del square u over del s square. Now we'll also substitute t as y, or we'll consider t as y. Now if we make this in this format, if we arrange it in this format, we have del square u over del s square minus del square u over del t square equals to 0. Now comparing it to the general formula, a is equal to 1, b is also not given, so b is equal to 0. Now c is equal to what? Negative 1. Now substituting that into the discriminant b square minus 4ac, we have 0 square minus 4 times 1 times minus 1, which actually gives positive 4. And 4 is actually greater than 0. Since 4 is greater than 0, the wave equation is an hyperbolic PDE. Types of boundary conditions. In numerical methods, the PDE handles what happens inside the system, but the boundary conditions dictate exactly what is happening at the physical edges of your domain. So one of the boundary conditions we'll be dealing with is the Dirichlet condition. It describes the exact value of the value itself at the boundary, and the idea behind it is that the function is set equal to a known constant or a specific coordinate function at the boundary edge. The initial variable is equal to the value at the initial point, and the final variable, this c subscript l, is equal to the value at the final point. And for the second boundary condition, we have the Newman condition. It describes the derivative, that is the gradient of the variable across the boundary area, and the math behind it is that instead of knowing the variable c, you are given the rate of change of c with respect to a particular space evaluated exactly at the boundary limit. So this is just the mathematical denotation for it. And lastly, we have the Cauchy or the mixed condition. This describes a linear combination of both the variable's value and its derivative at the boundary, just like a combination of the Dirichlet and the Newman condition. So here, the idea is that it links the value and its slope together using known scaling coefficient AB to equal a targeted boundary reference value. And this is just a mathematical notation for it, where a subscript 0, a subscript l, b subscript 0 and b subscript l are known coefficients. Moving on to finite difference method. There are several numerical methods of approaching PDEs, but one of the most common and foundational one is the finite difference method. It can also be called FDM. FDM is a numerical technique used to solve differential equations by approximating continuous derivatives with algebraic finite differences. The core objective is to take a complex calculus problem and turn it into a straightforward algebra problem that a computer can solve in milliseconds. FDM are suitable for simple geometries like rectangles, but it is awkward for complex irregular shapes. When it comes to irregular shapes, methods such as FEM, that is a finite element method, can be used, and there are also other methods like the FVM, that is the finite volume method. The first step FDM approach are: 1. Discretize the continuous physical domain into a discrete grid or mesh. 2. Approximate the exact derivatives in the PDE using algebraic finite difference approximations. 3. Substitute these approximations back into the PDE to generate an algebraic finite difference equation. And lastly, solve the resulting system of algebraic equations. Let's look at anatomy of a mesh grid. Consider a graph of x against y with a scale of 1. So we can say our s, on the x-axis we have 1, 2, 3, and on the y-axis we also go from 1, 2, 3. So the difference between this s and the y units is known as the h, which is the mesh size. And looking at this shape here, we can call this the curve, which actually gives the boundary condition. Then the region in which this curve occupies in the graph is called region or domain. Now the points that are plotted, like the points where s and y meet, are either interior points or boundary points. So let's look at how to label them. Looking at this one here, the point that at this point where s is equal to 1 and y equal to 0, it will be labeled as what, p10, because according to notation or graphical notation, we label according from s to y, s before y. Now for this point where s equal to 2 and y is equal to 0, it is labeled as p20. Now looking at this one upward here, at this point s is equal to 2 and y is equal to 1, so that is what, p21. This is at this point s is equal to 1, y is equal to 1, this is p11. Now in between this curve or this region, the points that can extend into 4 different places are known as nodes. For example, this p22 can extend to the right side, it can extend to the left hand side, it can extend to the upward, and it can extend downward. In between this region, it has value across 4 cardinal places, or 4 cardinal points rather. Now let's represent s and y as ij notation. Now let's say this is a point, a node in our region Pij. When we extend to the right hand side, it means we move to the positive x-axis. Now we'll add 1 to the s notation. That is, if it was p22, let me use this one. If it was p21 before and we extend to the right hand side, now 2 plus 1 will be what? That is p31, because we move positive to the x-axis. Now from that particular point, when we move to the left hand side, that is to the negative x-axis, we'll subtract 1 from the I notation, that is pi minus 1 comma j. Now from that point also, when we go upward, that is to the positive y-axis, we add 1 to the j notation, and we will go downward from a point, that is we subtract 1 from the j notation, that is to the negative y-axis. Now interior and boundary point, what are the differences? Interior point, a node where all 4 of its closest neighbors, up, down, left, right, are also inside the region. I explained that already. So example of a node in this particular graph here is what, p1, p22, yeah, p32, p21, and p31. Let's look at the difference between an interior point and a boundary point. A node where all 4 of its closest neighbors, that is up, down, left, right, or just like north, south, east, west, are also inside the region, is known as the interior point. So example, for in this particular region here, we have p22, we have p32, we have p21. Their north, south, east, west points are also in the region, so those are interior points. Now for boundary points, nodes that lie on or right next to the bounding curve. These are just like the points that are at the circumference. For example, p10, p20, it does not extend to 4 different points. It can only extend to, I think, maximum of 2. Yeah. Now, derivation of finite difference method for Laplace equation. Using the second order central difference approximation, we get 2 standard formulas derived from Taylor series expansion, which are in the x direction and in the y direction. So for the x direction, it is represented as del square u over del l square, approximately equal to the function u in respect to x plus h, comma y, minus 2 multiplied by function u in respect to sy, plus function u in respect to x minus h, comma y, all divided by h square. And in the y direction, we have del square u over del y square, approximately equal to the function u in respect to s comma y plus h minus 2 multiplied by function u in respect to sy plus u in respect to s comma y minus h, all divided by h square. We can then apply it to Laplace equation, which is the sum of del square u over del l square and del square u over del y square. By adding the two equations, we can observe that 1 over a square is a common factor. So we have 1 over a square all in bracket of u of s plus h comma y minus 2u of s comma y plus u of s minus h comma y plus u of s comma y plus h minus 2u of s comma y plus u of s comma y minus h. All of these are just functions changing in its coordinate points. Now when we collect item, we will observe that negative 2u of s comma y appears 2 times, so we have negative 4u of s comma y. We will multiply both sides by h square to eliminate the 1 over h square fraction. Now we'll be left with the sum of the function equal to 0 as our equation. Then we'll switch to grid notation, that is, let s equals I and let y equals j. Now for example, let's pick a center point at u subscript sy, which can be written as u subscript ij or u of ij. Now from this particular point, if you move towards the east direction, which is to the positive s axis, it means the position of the s will increase by a number, right? So that is how we arrive at u of s plus h comma y. So only the s will increase, the y will remain constant. So it can also be written as u of I plus 1 comma j. Also at this particular point, this center point, if you move to the west direction, which is the negative s axis, you have a u of s minus h. There will be a decrease in the position of s and the y will still remain the same. So that is also equivalent as u subscript I minus 1 comma j. And also from that particular point, if we move upward, that's to the north direction, which is also the positive y axis, there will be an increase in the position of y. So it is u of s comma y plus h, which can be written as u of I comma j plus 1. And if we do the same thing to the negative y axis, then there will be a decrease in the j notation. Now when we substitute the index into the formula, where s equal to I, h equal to 1 and y equal to j, we'll have this. Then we can make uij the set of formula, which is the center point. Now uij, okay, negative 4uij to the other side, we have a positive 4uij. Now the finite difference equation for Laplace equation can be given as the center point uij equals to u of I plus 1 comma j plus u of I comma j plus 1 plus u of I minus 1 comma j plus u of I comma j minus 1, all divided by 4. And this is a formula, standard formula, called the finite difference equation, and you can observe the pattern in it. Now once we have successfully derived our system of algebraic equations using the finite difference method, we have two distinct pathways to solve them. Either we use the direct method or the iterative method. The example of a direct method is the Gaussian elimination or the LU decomposition of solving matrix. So we can use this to solve the whole system at once, or you can also use the iterative methods like the Gauss-Seidel method to solve the equation step by step through repetition. Now for our example 1, it says the four sides of a square of side 12 cm made of homogeneous material are kept at constant temperatures 0 degrees Celsius and 100 degrees Celsius as shown below. Using a mesh wide grid of mesh 4 cm and applying Leibniz's method, which is Gauss-Seidel's integration, find the steady state temperature at the mesh point. So this is the diagram given. It implies that at the boundary condition at the left and the right hand side are equal to 100 degrees Celsius, and at the bottom we have a boundary condition of 100 also, but at the top we have a condition of 0, boundary condition of 0, yeah. And our step size, or mesh size rather, is equal to 4. So when we split this rectangle into 3 parts, we have 4, 8, 12, because they said it is a 12 by 12 material. We divide the rectangular region into 3 horizontal parts and 3 vertical parts. We arrive at 9 buses and 16 points. Of all the 16 points, only 4 are nodes. The nodes are the one at the middle, which are the P12, P22, P11, and P21. I wrote it here in the function, in U function. And the boundary are the one at the edges, which are the U10, U20, U31, U32, U23, U13, and so on. So for the nodes, we'll calculate them using the finite difference. What's E again? Using the finite difference equation. Now applying the FDE formula to node U11. So according to the formula, from this central point, when we move to the positive s-axis, the position of s will increase, right? So that is U21, plus when we move to the negative s-axis, the position of s will decrease by 1, that is U01. When we move to the positive y-axis, the position of y will increase by 1, that is U12, plus when you move to the negative y-axis, the position of y will decrease by 1, that is now U10, all divided by 4. Now you just substitute the value for these points. So using the mesh diagram, U21 is this. It is unknown. It is also a node point. U01 is at the boundary, so that is 100. It is given as 100. U10 is also at the boundary. It's given as 100. So only U12 and U21 are unknown because those one are also node points. So we have U21 repeated plus 100 plus U12 repeated plus 100 divided by 4. Now making dividing all. Okay, when we add the two constant, that is 200. So divide all by 4. We have U11 equal to 0.25 multiplied by U21 plus 0.25 multiplied by U12 plus 200 divided by 4 equals to 50. So that's our equation 1. What we'll do is apply the same formula for the second node, which is U21. This is U21. So U21 will be equal to U31 plus U11 plus U20 plus U22, all divided by 4. That's just how to apply the formula. Now we substitute the value, and of all the 4 points, only U31 and U20 we have a definite value, which is 100, because they are the boundary points. So when we divide all by 4 also, we arrive at U21 equals to 0.25 U11 plus 0.25 U22 plus 50, and that will be our equation 2. So we do the same thing for node U12 and we do the same thing for node U22, and I hope that is easy to catch now. So for U12, this is the equation, our equation 3, and for U22, that is the equation 4. So now we have 4 equations all together. Now we can represent the function with an unknown variable s. So let s1 equal to U11, s2 equal to U21, s3 equal to U12, and s4 equal to U22. We can rewrite the 4 equations again in this form. Now we'll be using Gauss-Seidel iteration to solve this algebraic equation. And how do you go about that? The first step is to start with initial guess. Let s1 equals s2 equals s3 equals s4 and equals to 0. We start with 0. Now to calculate s1 using the equation above, we substitute the value for s2 and s3 as 0, 0, because that's all we have here as our first value. So we have s1 equals to 0.25 multiplied by 0 plus 0.25 multiplied by 0 plus 50. And we'll add that together, we get 50. That will be our new value for s1. Now our s2, when we want to calculate for s2, we have two variables, s1 and s4. Now that we already have a new value for s1, we'll be using that new value. So to calculate s2, we'll use the new value for s1, which is 50, and the old value for s4, which was initially 0. Now we'll substitute that into the equation. We have 0.25 multiplied by 50 plus 0.25 multiplied by 0 plus 50 constant here, and that will give 62.5. Now we have a new value for s2. Now to calculate s3, we need two variables also, s4 and s1. S4 is still unknown, like we have just the old value for it, while s1 has a new value. So we'll be using the old value for s4, which is 0, and the new value of s1, which is 50. Substituting this into the equation, we have 0.25 multiplied by 0 plus 0.25 multiplied by 50 plus 25, which gives 37.5. Now, to calculate for s4, we need two variables, so s3 and s2. So s3, now we have a new value for s3, which is 37.5. We'll be using that. And also we have a new value for s2, which is 62.5. When we substitute those two values into the equation 4, which is 0.25 multiplied by s3, which is 37.5, plus 0.25 multiplied by s2, which is now 62.5, plus 25, this gives 50. So this new set of value are what we use for the next set of integration. So for the second loop, we go again. We calculate s1 using the same equation. We'll be using the new value for those variables s1, s2, s3. So by the time you do that consistently, we'll arrive at this table. You fill in this your table. This is how we do the integration method until we arrive at a convergence point. A convergence point is when we now start having symmetric values. Like for example, now after the 8th and 9th integration, we can observe that s1 equals to 87.50 and 87.50, like they are equal, they are alike. S2 is also alike, S3 is also alike, and S4 is also alike. So at this point, we can say that our value for s1 equals to this, s2 equals to this, s3 equals to this, and s4 equals to this, which is what I wrote here. For example 2, it says solve the boundary value problem for del square u over del L square plus del square u over del y square equals to 0 for 0 is less than s less than 2, which means the value of s in the ranges from 0 to 2 in the s axis, and 0 less than y less than 2, that means for our y axis it ranges from 0 to 2. Now when we have our rectangle and we split it into 3, the upper boundary here is giving us 2, both for the s and the y axis, which means our h, which is this mesh size, it is 2 divided by 3, because we split 2 into three places. That is our s1, this point here, this is s origin and y origin, s naught, this is s1. So our s1 will be 2 over 3, s2 will be 2 over 3 plus 2 over 3, that is what, 4 over 3. Then s3 equals s subscript 3 equal to what, 2. Now at this point 2, y1 will be what, 2 over 3, y2 will be 4 over 3, and y3 is 2. Now we are given some boundary conditions in the questions. It says that for a function that has its s ordinate as 0, irrespective of the y value, it is equal to 0. That boundary condition for that particular function or point is equal to 0. Also, for a function or a point whereby the y ordinate is equal to 0, irrespective of the s value, then it is also equal to 0. Because what we'll notice is that in this particular question, they didn't give us the left hand side, right hand side, and bottom as 100. So we have to look for the boundary value for each of the boundary points. And we have 8 boundary points in these questions, which is this P02, P01, P10, P20. We have to look for them individually using the boundary conditions that we're given. Now the other condition is that for a function of u whereby the s ordinate is equal to 2, irrespective of the y ordinate, then the value for that particular point will be calculated as y multiplied by 2 minus y. And also for a function whereby the y ordinate is equal to 2, irrespective of the s ordinate, the value of that point will be calculated as s if it applies to this condition, that means s is greater than 1 and s is greater than 0, and it will be calculated as 2 minus s if s is greater than 2, or s is greater than or equal to 1. Now calculating the boundary values, moving across the grid in steps of 2 over 3. As I said earlier, that s naught and y naught will be equal to 0, s subscript 1 and y subscript 1 equal to 2 over 3, s subscript 2 and y subscript 2 equal to 4 over 3, and s subscript 3 and y subscript 3 equal to 2. Now let's calculate the bottom boundary. The bottom boundary is the position whereby our y is constant, y is 0. It is only the s that is dynamic, that is changing. So, and we have 2 points at this particular bottom, at this particular boundary, which is P10 and P20. And we have a condition that says that a point whereby the y ordinate is equal to 0, irrespective of the s value, then that particular point is equal to 0. Therefore, P10 at 2/3, 0, because P10 is located at 2/3, position 2/3, 0. P20 is located at position 4/3 of 0. So both of them are equal to 0 according to this condition that was given. For the left boundary where s equal to 0, this is the left boundary. S equal to 0 because it is constant, only y is dynamic. So according to the condition given, that a point whereby the s coordinate is equal to 0 irrespective of the y value, then that particular point is also equal to 0. Therefore, the point P01 and P02 are both equal to 0. And for the right boundary where s equal to 2, this is the right boundary here where s equal to 2. So according to the condition given, it says that where a point whereby the s ordinate is equal to 2, then the value of that point will be calculated using y open bracket 2 minus y. So whatever the y value is, we substitute it into this function. Now our point P31 lies at which point? It lies at point 2, 2/3. That means the y value is what? 2/3. So when we substitute y as 2/3 here, we have 2/3 open bracket 2 minus 2/3. So that gives 2/3 times 4/3, which is equal to 8/9. Also, when we do the same thing for point P32, this one lies at point 2, 4/3. When we substitute 4/3 into the function y open bracket 2 minus y, we get 8/9 also. Now for the top boundary where y is equal to 2, we have 2 points also, P13 and P23. So for the P13, let's say according to the condition that said that if the y ordinate is equal to 2, then we can apply either of these two conditions based on the wherever it falls to abi. So P13 equals to, let me see, P13 lies at point 2/3, 2. So 0.2/3, 2. Now the s value is actually 2/3, and it is greater than 0 and it is lesser than 1. So we'll be using this function for it. So that particular point will be equal to s, so which is the s value as 2/3. Now for P23, which lies at 4/3, 2, because the value s 4/3, it is lesser than 2 and it is greater than 1. So we'll be using this condition, which is 2 minus 1. So 2 minus the value of that, 2 minus s rather, 2 minus that value of s, which is 2 minus 4/3, actually gives 2/3. Now we have solved for all our boundary points. Now we set up the FDE, that is the finite differential equations. So starting with the first node u11, we have the formula u12 plus u21 plus u01 plus u10/4. All we just have to do is to substitute the value for these points, because we already have them now. We have those points in our notes. Now u11 will be equal to, when we divide all by 4, we have 0.25 multiplied by u12, that is also another node, plus 0.25 multiplied by u21, another node, which means boundary or points u01 and u10 are actually equal to 0, and this is it here. Yeah, u10 and u20 are equal to 0. Now setting up the finite difference equations. Calculating for the first node u11, the formula goes as, let's use the mesh. So if this is u11, the formula is equal to, just by going to the 4 axes along this center point. So this is what u21 plus u01 plus u10 plus u12, all divided by 4, and we'll substitute the boundary points. So u01 and u10 are both boundary points, and it is equal to 0. This is u01, no, this is u10, which is equal to 0, and u01, which is equal to 0 also. So divide all by 4, we have u11 equals to 0.25 u12 plus 0.25 u21. That's equation 1. So for equation 2, we do the same thing for node u21. U21 is, where is u21? This is u21. So it is equal to u31 plus u11 plus u20 plus u22, all divided by 4. Where is it? This is it. So when you substitute the boundary point, also u31 equal to 8/9 and u20 equal to 0. The 8/9 plus 0 constants add up as 0.22. So divide all by 4, we have u21 equal to 0.22 plus 0.25 multiplied by u22 plus 0.25 multiplied by u11. That is equation 2. So you do the same thing for u12 using that same logic to get your equation. Do the same thing for u22 using that same logic to get your equation. So we arrive at 4 equation. Now you can say let s1 equals to u11, s2 equal to u21, s3 equal to u12, and s4 equal to u22, and we write your equation in this form. So I converted the decimal point to fraction, and now using the Gauss-Seidel equation again, the iteration method, we'll start with an initial guess that s1 equals to s2 equal to s3 equal to s4, which is equal to 0. Now we substitute 0 to calculate s1. We substitute 0 into the two variable, unknown variable, which is s1 s3. So let's try that together. So s1 equals to 0.25 multiplied by 0 plus 0.25 multiplied by 0, which is the value for s3 also, and that actually gives 0. That means our new value for s1 is equal to 0. We'll fill that in our table. Like, we write the first 0, the initial guess first. Now the new value for s1 is 0. We'll fill it under the column for s1. Now we'll calculate s2 using the formula, which is 0.25 multiplied by s1, which is the new value of s1 as 0, plus 0.25 multiplied by s2. We don't have a new value for s2 yet, which is still the old value, which is 0, plus 2/9. When we add this together, we have 2/9. So we go to our table again, we fill in 2/9 under s2 colon. Now for s3, we apply the formula 0.25 multiplied by s1. So the new value for s1 is what? Is still 0. We'll put that there, plus 0.25 multiplied by s4. We don't have a new value for s4 yet. We use the old one, which is 0. We add it, plus 1/6, and that gives 1/6. You go to the s3 column, you fill it by 1/6. Now for s4, we have 0.25 multiplied by s3. So we have a new value for s3, which is 1/6. You replace s3 as 1/6, plus 0.25 multiplied by s2. We also have a new value for s2, which is 2/9, plus 7/18. So when you add this together, we should have 35/72. You go to your table, you fill it as 35/72. So now you go again, start again, do another iteration loop for s1 equation using this new set of values of s1, s2, s3, and s4, and you keep filling out the table until you arrive at similar answer in the same column. So if you notice, when you check your calculator, these big fractions here are this second to the last column are actually equal to the simplified fraction below. The final converged solution gives u11 as 7/36, which is approximately equal to 0.1944, and u21, which is equal to 5/12, approximately equal to 0.4167, and u12, which is equal to 13/36, approximately equal to 0.3611, and finally u22, which is equal to 7/12, approximately equal to 0.5834. And that is our final example. So you can take this exercise, which says you should find the approximate solution of the Laplace equation at the interior point of the given region. So you have this region for s and y axis. So you notice that, okay, they gave us a mesh size of 1, that h is equal to 1. Since our y can only exceed to 2 and our s can only exceed to 3, it means you get a rectangle made of 3/2, which is equal to 6 boxes in total, and you end up with 2 interior nodes, and you might not actually have to deal with 4 simultaneous equations. Don't forget to subscribe to the channel. You can drop your solution in the comment section. Also, the link to this lesson file will be provided in the description section. Thank you for learning with me.